All right, so last time we're looking at how the strong nuclear force can cause nucleons to bind together and overcome the repulsive effects due to the protons that tend to make the nucleus want to fly apart. And so we can look at a reaction that tends to spontaneously go, and we find that these reactions tend to have a number of protons in the nucleus that's less than number 26. And so number 26 is the atomic number for iron. And so we're going to talk a little more later about why that's true, but it turns out that what we call fusion can happen for these elements. And so fusion then, as opposed to fission, which we were talking about last time, is the combining together of smaller elements into bigger ones, as the term might imply. Okay, and so that's a fusing together of smaller elements into big ones. But that can produce energy, provided that we're not getting any bigger than iron. Iron turns out to be the limit of our stability for fusion. And so we can also talk about the process by which one of these reactions can take place. And so here, we're using the notation that this is our element, okay? And so X is our element. The proton number is in the lower left-hand corner. The neutron number is in the lower right-hand corner. And the atomic mass number is in the upper left-hand corner. Now, there are many other different alternative formulations, but this is one that I'm used to. All my notes are in this, and so I'm going to write it this way. So A then, our atomic mass number, is equal to Z plus N. So that's the number of neutrons plus the number of protons equals the total number of nucleons in the nucleus. Okay, and so here, a single proton then would be a hydrogen atom. That would have one proton, 0 neutrons, and 1 plus 0 nucleons. And so let's say that in a spontaneous reaction, this, by the way, is something that you'll be doing in Lab 6 this week, is adding neutrons to protons and seeing which ones are stable and which ones aren't. It turns out that heavy hydrogen is stable. Okay? And so this will give off energy then, meaning that we've gone to a lower energy state. So this is like atomic transitions, where if an electron is in a higher energy state and it drops down to a lower energy state, it gives off energy. Well, this is going to happen here too. Okay? And so there's going to be energy released by this reaction. And we'll call this kind of energy the binding energy for the reaction. And so the way then that we can determine the binding energy is by first of all noting that the binding energy has as its source mass. Okay, and so the difference in mass times the speed of light squared, delta m c squared, is equal to our binding energy. Okay, and so when you weigh, in other words, the hydrogen atom and the neutron, and you compare that in weight to the heavy hydrogen is going to pop up on the scale. So here's our heavy hydrogen, 1, 1, 2 on this side, and then on this side we've got our regular hydrogen and our neutron, 0 protons, 1 neutron, 1 nucleon here. Okay. Then this side pops up, this side goes down, because this side is heavier. there's more mass in this situation, but it goes to a lower energy state, and so some of that mass is converted into energy. And so that is the whole process by which our sun produces energy too. That's this fusion reaction. But in that case, it's turning hydrogen into helium. So here I'm just looking at a simple example. We're just taking a hydrogen atom, we're adding a neutron to give us heavy hydrogen, which has 1 proton and 1 neutron. And we observe that that gives off energy. And so we could prove that this is right, that if we can compare the difference in the rest energies of these particles before and after the reaction. So this is the rest energy then of the heavy hydrogen. Okay. And this is the rest energy of the, let me just see that I've got that the way I want it here. Actually, let's start with this, because this is going to be more massive, and subtract that away from it, like that. That's what I really wanted to do. Because this one is going to be more massive, this one is going to be less massive, and so that'll give rise to a positive number here. So what we're going to need to do then is look up the masses of each of these individual quantities. And when we do that, this will give us a difference in mass multiplied by the speed of light squared. When that's done, we end up getting 2.224 MeV. Now how do we do this? Well, we need to have tabulated values for the mass of the proton and the mass of the neutron, and also for the mass of the heavy hydrogen. And so this reaction then is, because this mass is greater than this mass, and then we multiply that by the speed of light squared, we end up getting this value for the binding energy. Okay? And so that's great if somebody already tells you that that's what it is. But how do you go about figuring out the binding energy in terms of tabulated values? Well, let me do it for kind of our transition element. This is the one that is the most stable in the universe. So what we might ask ourselves is, in the state of the nucleus in which we have the iron atom, how is the weight of that iron atom related to the weight of all the little protons and neutrons that are separated that make it up? And so when we do this, what we find is that we have to take it apart and look at the masses of all the individual pieces. Okay, so here, iron has an atomic number of 26, or in terms of the number of protons. It's got a few more neutrons than it does protons, because we are larger than element number 20. Remember in the last lecture we said around element number 20, you start needing more neutrons to cement together the nucleus with a strong nuclear force. So that this nucleon number is number 56. Okay, and so what we need to do then is compare the masses of 26 protons and 30 free neutrons to the mass of the iron atom. So, and that'll be our binding energy. So our binding energy then will be equal to the mass of 26 hydrogen atoms. So this is 1, 0, 1, plus 30 times the mass of the neutron. Times c squared, minus the mass of the iron atom, which is 26 Fe 30 56 times c squared. Okay. And so we can factor out the c squared from all of these. And so what we end up with here then is 26, and the mass of a hydrogen atom. This has to be given to you. And so this is in terms of what we call atomic mass units. The mass of the hydrogen is 1.008 007, sorry, 825 mu, where mu is called our atomic mass unit. And it's approximately equal to 1.67 times 10 to the minus 27 kilograms. So everything's written in terms of atomic mass units. Then the mass of our neutron, a single neutron, would be 1n01. And that is slightly larger because a neutron is a proton plus a nuclear electron. So this becomes 1.008665 mu. Now, if you just carry this out to 3 significant figures, you'll notice that there's no difference between them. So you have to carry your calculations out to this many significant figures, or else you won't get the right answer. So you want to be really careful about that. And then the value for the mass of the iron nucleus and that is equal to 55.93493. Mu. Okay. So we might wonder here, well, is this really the mass of the nucleus, or is this an atomic mass with all the electrons circling around? And the answer is, well, it's an atomic mass, not a nuclear mass. And so that means that in these calculations, we are saying that the mass of the orbiting electrons is insignificant in relationship to the mass of the nucleons, which is approximately true, because when we look at energy states within an atomic structure, we're just dealing with energies on the order of electron volts, like it's minus 13.6 eV over n squared for a hydrogen atom, for example. Whereas here, our binding energy, even for a very modest kind of a reaction, like a proton and then adding a neutron to it, gives you millions of electron volts. Okay, so this is a factor of 100,000 greater. Now, why don't we just use the nuclear mass instead of having to kind of bite the bullet on this error that's produced by using the atomic mass? And the answer is, you can never get a free nucleus with all the electrons removed. It takes too much energy, so you just never be able to do it. So it's much easier to measure atomic masses than just say, well, it's not really significant in relationship to the nuclear mass. And then when you subtract these off, you're subtracting off a little bit of your error as well. But these are, in fact, atomic masses and not nuclear masses that we're looking at, particularly for these heavier elements. So what we need to do next, then, is to put in the masses, and then we'll factor out the c squared. So this is 26 times the mass of our hydrogen. So that's going to be 1.007825 mu plus the mass of the 30 neutrons. So it's like we've taken little tweezers and we've pulled out all the protons and the neutrons, and then we weighed them all when they're separated from each other by a large amount, and we determined that that's the total mass. So this is 30 times 1.008665 mu. And then we subtract off from that the lower mass iron, because this is in a more stable state. Okay, and so why does that mean a lower mass? Well, when it's in a more stable state, basically if I wanted to pull apart all of these iron atoms, it would take energy to pull off all those protons and neutrons. And so that would put all of the pieces at a higher state of potential energy. But something that has a higher state of potential energy has not only more energy, but it has more mass, by E equals mc squared. So by having more mass, it has more energy, and so that energy came from pulling these things apart. And by adding that extra energy to these things, by pulling them apart, you give them more mass. So when you work in the other direction, you take those pieces, you put them together, and the difference in mass is released as energy. Just the same way as an electron would take energy to accelerate it to a higher energy state, but would give off energy if you let it go to a lower energy state. So here we're letting it go to a lower energy state, and the most stable energy state of all is the iron nucleus. That's when they're at the happiest. They're at the lowest state of energy that they can be. So it's like this pin. This pin is the happiest in this system when it's on the surface of the table. Okay? That's the lowest energy it can get to that's accessible to it, unless I let it roll off onto the floor. Okay? And so the same thing with these. The lowest energy state that these protons and neutrons can get into, turns out, is a bunch of iron nuclei. And so the iron nucleus then, from this value here, is 55.93493 mu. Then that's all multiplied by c squared. Now, the way that I'm going to write c squared here is mu c squared. I'm going to write as an energy. And so this is in MeV, it's equal to 931.5 MeV. So therefore, I can write the speed of light squared as 931.5 MeV over mu. And then the mu units are going to cancel. So usually I don't like using those kind of units, but it's so convenient here that it doesn't make sense to do it any other way. So here then, the c squared, which was factored out of all of these terms, becomes then our 931.5 MeV over mu. And then the mu's cancel all the way through, and we just get a pure number. So what is that number? Well, for the iron nucleus, that's 492.5 MeV. So this is then the most stable element on the periodic table. But that's the same thing as saying that its binding energy per nucleon number is the highest. Okay? And so how would we calculate that? Let's go over to this board, and let's calculate the binding energy per nucleon for heavy hydrogen. So what is this? This is the binding energy per nucleon. So for hydrogen, being turned into heavy hydrogen, it does release energy. In this case, the binding energy per nucleon would be 2.224 divided by 2, right? Because the nucleon number for heavy hydrogen is 2, right? And so that would be 1.112 MeV over mu. So that's not very hot. But what about for the iron atom? So for iron, it's going to be equal to 492.5 divided by what? What's our A value for iron? 56. Good. So that's divided by 56. And so then that gives us .791. MeV over per nucleon. Okay, so we see that that's a lot higher binding energy per nucleon than for heavy hydrogen. Okay? And as we go to larger values, what we find is that these larger values do not end up giving us a positive value for B anymore. Okay? So what will happen then, as we start trying to fuse even heavier elements than iron, is that the mass of the iron nucleus here, as we start increasing this to elements that are beyond iron, is that it will cause the binding energy to go negative. Okay? And so, in other words, long story short, iron is the most stable element. And so if we plot the binding energy per nucleon for all elements on the periodic table, here's B over A, and then here is the atomic mass number, A. What we find is that it goes up like that and then it drops back off again. So this is our point of greatest stability. Then this number here then would be element number 56. Or if we plotted it in terms of Z, this would be element number 26. And this would be our iron value, which is 8.791. And then down here at number 2, we'd have our binding energy per nucleon for heavy hydrogen. That would be 1.112. And so anything up to here then means that as these processes go from hydrogen up to iron, we get energy is gained by fusion. But once we get to iron, we start going past iron, then on this side, energy is gained from natural radioactivity. Either natural or fission, as we talked about last time. Remember, they're not the same. So it may seem funny to think that at a nuclear power plant, our uranium-235 here is going to gain energy by busting apart into smaller elements like strontium and cesium and those kinds of things. But on this side, you gain energy by becoming a smaller element. Okay, because we're at our most stable point here, and so to try to get back to that most stable point, this is the lowest state of energy. And so you can do that then by breaking particles apart when they're bigger than iron. But you get that energy by putting particles together when you're less than iron. And so energy then is gained by fusion in this range. Energy is gained by natural radioactivity or fission when you're in this range. And so this then helps us to explain the way in which stars are born and die. And so what I invite you to do is look at the next video in the sequence, which will be the astronomy video that I just made on the evolution of stars. And that will give you actually more information than you need, but will be a very good example of how elements are made on the periodic table and how you gain atomic size as stars go through different aspects of the fusion reaction.